Welcome back. Section 4.6 is a very important section. It's on basis and dimension. Let's start with the definition. The vectors v1 through vn in a vector space V are said to form a basis for V if span of v1 through vn is your vector space V and the set v1 through vn is linearly independent. So in the previous sections, most recent sections, we learned the meaning of span and we learned the meaning of linear independence. So a set of vectors v1 through vn is a basis if it does two things. It spans your vector space and is linearly independent. Okay. Remark. If the set v1 through vn is a basis, then the vectors are distinct and non-zero. First of all, if you have seen in the previous section, if any vector repeats, then the set is not linearly independent. Well, if you're a basis, you must be linearly independent, so no vector must repeat. Similarly, we have seen in our previous section that if zero vector is in your set, then it is not linearly independent. Since your basis must be linearly independent, you cannot have any zeros. Second remark, the definition of a basis also applies to an infinite set of vectors. Alright? So instead of just stopping at n, you could have infinitely many vectors. If the span of that set is V and the set is linearly independent, then it is a basis. It doesn't matter whether you are finite or infinite. In essence, a basis is a minimal spanning set. First of all, it has to span. Secondly, if it is minimal, if you remember, a minimal spanning set by definition is also linearly independent. We had seen this earlier. Consider the column space R3. Remember, R super 3 stands for columns of size 3. So you're looking at all columns of size 3 where entries can be any real number. Now look at this. To get A, B, C, any vector, you need at least the following three vectors: 1, 0, 0, 0, 1, 0, 0, 0, 1. Why do you need that? To get that position A, you need 1 here, 0, 0. To get that position B, you need 0, 1, 0. To get the position C, you need 0, 0, 1. This is the minimum collection of vectors you need to span all of R3. So this potentially, we haven't proved anything, we are just talking. This is potentially a basis. Okay. Let us check whether it is indeed a basis. Alright. First of all, any vector ABC can be written as A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1. Exactly what we were talking about. Any vector ABC can be spanned by these three vectors. Therefore, span of v1, v2, v3 is the entirety of column space R3. Now let's check for independence. Notice you need span and you need independence. Let's check for independence of v1, v2, v3. Suppose you have some real numbers a1, a2, a3 such that a1, v1 plus a2, v2 plus a3, v3 is the vector 0 vector. Then a times v1, 0, 0, a1 times 1, 0, 0, A2 times 0, 1, 0 plus A3 times 0, 0, 1 is the 0 vector 0, 0, 0. What does that mean? That gives you A1 here and nothing below. This gets you A2 here and nothing else above. This gets you A3 in the bottom and nothing else above. So adding these multiple vectors, you get A1, A2, A3 should be equal 0, 0, 0. What does that mean? A1 has to be 0, A2 has to be 0, A3 has to be 0. That is, we started with a linear combination of these three vectors resulting in 0 vector. What is our conclusion? The coefficients have to be 0. That's the only possible solution. Therefore, the set is linearly independent. So you have the span and you have the linear independence. Hence, the set V1, V2, V3 is a basis of R3. Now consider the row space, not column space, excuse me, ABC, row space. To span the row space, we need at least these three following vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. Exactly the same arguments as before. You may check that this is a basis, exactly the same. The proof is identical to what we saw. Now the base is 0, 1, 0, 0. So these are the column vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 of the column space, or the base is 1, 0, 0, 0, 1, 0, 0, 0, 1 of the row space. These are called the natural bases. It is natural because you just look at it and you know you need these three vectors. Okay, so these are called natural basis or the standard basis. So in future when we talk about standard basis or natural basis, if it's column, we are looking at these columns. If it's row space, we are looking at these rows. In general, suppose you have an n column space. So you have dimension n. The natural basis or the standard basis, these are specified notations, E1 through En. These are specified notations where EI stands for that column with 1 in the ith location and zeros everywhere else. EI has 1 in the ith position and 0 everywhere else. That is your natural basis. Collect. So what does that mean? E1 has 1 in the first location, 0 everywhere else. E2 has 1 in the second location, 0 everywhere else, and so on. En has 1 in the last location and 0 everywhere else. That's what this symbol represents. So these are natural or standard. In other words, these symbols are reserved for precisely for such columns. Likewise, for the row space, EIs represent those rows. EI is that row with 1 in the ith location, 0 everywhere else. Okay, so these are natural basis or standard basis. Special case, when n is 3, we write, so this is very special. E1, E2, E3, they have other names. E1 is called I, see boldface I. E2 is called boldface J. E3 is called boldface K. This is in special case when n equals 3. Alright. Likewise, for row space, I is E1, J is E2, K is E3. Same notion. Alright. Now let's look at an example. Consider the subspace V of P2. P2 stands for polynomials of degree less equals 2, consisting of all the vectors of the form at squared plus bt plus c. Okay, so you're looking for all polynomials of degree 2 or less with the condition the constant c has to be a minus b. So this coefficient minus this coefficient must be this c. So in other words, your V, it is subspace of P2. It should look like at squared plus bt plus a minus b. A minus b being the constant term, which is a minus b. So what does this say? A and b can be any real number. To identify for a basis for v, so we are developing intuition, you see, because you will soon need to identify basis. To identify a basis for v, we look for a minimum spanning set. What is it at the minimum that we need? Look at that. This is my suggestion. So what have we done? You see, you are allowed a and b to be any real number, right? So I'm letting a equals 1 and b equals 0. Then I get 1t squared, 0t plus 1 minus 0 is 1. That's one polynomial. In the next case, I set a equals 0, b equals 1. So 0t squared, 1t, 0 minus 1. You see? So a and b can be any real number. So I'm just choosing a to be 1, b to be 0. That's the first polynomial. Then a equals 0, b equals 1. That's the second polynomial. So simplifying this, the first polynomial is t squared plus 1. The second polynomial is simply t minus 1. So this is my guess of a basis. Let's see. We claim that S is a basis for V. First, we have to show that it spans all of V. So remember V consists of polynomials which look like this. So let us take any polynomial from V. Then at squared plus bt plus a minus b is a times t squared plus 1 plus b times t minus 1. You can check for yourself. At squared, a, bt minus b. So you see, we've covered every coefficient here. Therefore, at squared plus bt plus a minus b, any polynomial you chose from V, is also in the span of S. In other words, span of S is all of V. Now we want to check whether S is linearly independent. Suppose you have real numbers a1, a2 such their combination, linear combination, is the zero polynomial. Okay, zero polynomial is just the zero constant polynomial. So multiplying, you get a1 t squared, a2t, I'm trying to maintain degree 2, degree 1, and degree 0, I get a1 minus a2. This is 0. This is the zero polynomial, which means a1 has to be 0, matching the degree. T squared coefficient must be 0. Coefficient of t must also be 0. Which means what? You started with a linear combination of these two polynomials to get 0. Turns out coefficients had to be 0. That means the set S is linearly independent. Therefore, not only does it span V, it is also linearly independent. Therefore, it is a basis of V. Now let us go through this definition. A vector space V is called finite dimensional if there is a finite subset of V that is a basis. So if you can find a finite basis of your vector space, that vector space is called finite dimensional. If you cannot find a finite basis, then that vector space is called infinite dimensional. In other words, no such finite basis exists for V, then V is infinite dimensional. Okay. If V1 through Vn is a basis for V, then multiplying V1, just one vector, by any non-zero scalar also gives you a basis. What does this say? There can be many different bases. You see, bases with the E is a plural of singular basis. If you find one basis, multiply any one of the vectors by a non-zero scalar. Actually, you could multiply any of the vectors with any non-zero scalars. Whatever you get will continue to be a basis. In other words, you have many different bases for a vector space V. We'll continue with this theorem in our next video.